I start from the last class here. So what we are doing is this. So there was a reaction H2 reacting with O2 giving water, and we were doing. I mixed 10 gram hydrogen, 10 gram hydrogen with 15 gram oxygen, 15 gram oxygen, and we want already balanced reaction here, 1, and here is 2. So this is already balanced. So they ask, okay, I mixed 10 gram of hydrogen with 15 gram of oxygen. How much water is formed, right? So first of all, we need to find the limiting reagent, and I told you how to find the limiting reagent. Last time, we did the limiting reagent calculation, and we found that oxygen is a limiting reagent. Oxygen is limiting reagent. Oxygen is limiting reagent. Limiting reagent, and it has only 0.47 mole. So 0.47 mole. So I'm going to write that limiting reagent here, 0.47 here, and I want to find how much water I from here, X, right? That's it. So I think I did some mistake in the last class lecture, and somebody pointed out, oh, there was some mistake, so I corrected yesterday and posted the PowerPoint slide again. So now we never do the limiting reagent from hydrogen because it is not, it is excess, it is the limiting reagent. So I just take the ratio, X by 2 is equals to 0.47 by 1. So X is equals to, this is, I don't know how much is that, 0.47 multiplied by 2 is equals to 0.94. So this goes here, divide by 1 gives 0.94 moles of water. Moles of water. So if you want to convert this moles to gram, so what you can do is 1 mole of water is equals to 1 mole water is equals to 18 gram. So you can convert this mole to gram. So this is moles, so 0.94 moles. So I want gram, so I put that gram part up there, and then I don't need mole, so I put that mole part down here, and I pencil mole there, and I multiply this and how many gram water I found, right? So most important is to find the limiting reagent. So I posted a homework 4 in the canvas. So I put one reaction there, and I am asking, oh, which one is the limiting reagent? How much product ammonia is formed, something like that. So you just try that one, yeah? So that's really important. Now, I take another reaction here, similar, exactly same thing, but different reaction. So the another reaction here is N2. So I'm in the slide number 4 in the lecture slide 2, lecture 2. So here is ammonia. So nitrogen plus hydrogen gives you ammonia. So this is slide number 9. So they are already balanced here, 3 here and 2 here, right? So this is the reaction, and the question is, if you mix 10 mole of hydrogen with excess nitrogen, excess nitrogen, excess means nitrogen is a lot, so it is not a limiting reagent, yeah? So you don't have to find the limiting reagent. What is the limiting reagent here? Nitrogen is excess, meaning that hydrogen is the limiting reagent, yeah? Make sense? So we don't have to calculate that for the limiting reagent because it says nitrogen is excess. Nitrogen is excess. So this is a lot. So we don't do any calculation from nitrogen. We need to do from the calculation from the limiting reagent. Nitrogen is excess, therefore the hydrogen is limiting reagent. So hydrogen is 10 mole. So how much ammonia is formed? Calculate the ammonia produced in moles and gram both. So this is X, right? Simple. So nitrogen, this is nitrogen is excess, so I don't need, we don't calculate from here. Hydrogen, therefore hydrogen is limiting reagent, so 10 mole is given. And how much ammonia is formed? So I need to find that X, right? So I'm just taking the ratio, X by 2 is equals to 10 by 3, and then you cross multiply here, 10 multiply 2 divide 3, so that gives you 20 by 3, which is 6.66 moles. So 6.66 moles of ammonia is formed, right? Now, how to convert these moles to gram? You already know. Now, 1 mole of ammonia is equals to 1. Look at the periodic table. 1 mole ammonia is equal to nitrogen is 14, hydrogen is 1, 14, 15, 16, 17. So 17 gram. 17 gram. So 1 mole of ammonia is equal to 17 gram. So if I want to convert this mole to gram, so I have 6.6 moles here, 6.66 moles. So I put this factor in such a way that I want to cancel the mole part. So I put 1 mole down here and then gram part up here. So mole cancel. So you multiply this with this one and then you get the gram, right? 6.66 multiplied by 70. That many gram ammonia is formed. Good. Now let's go to the slide number 5. Slide number 5. So in the slide number 5, it is giving this equation here. So in slide number 5, it is giving C6H12O6. So this is a sugar, table sugar, which we eat in kitchen, C6H12O6. And this is, there is balance, there is 1, and then there is O2. O2 in balance, number 6 is there, and then we go to 6CO2 plus 6H2O. So this is already balanced. This is a balanced chemical reaction, right? Now, it is saying I bond 250 grams of glucose in oxygen. So oxygen is a lot. So oxygen never finishes. So what is the limiting reagent here? Glucose is a limiting reagent. Yeah. So we don't have to calculate which one is the limiting reagent. They are saying I have some glucose which is 250 gram glucose. This one, and then I bond that with a lot of oxygen. Oxygen never finish. So this is excess. So I don't do calculation from here. This is excess. Yeah. So I need to do calculation from here. Now how much is this one? 250 gram. Now I convert this into moles, right? So it's given here. 1 mole is equals to 180 gram. So 1 mole glucose is equals to 1 mole of this glucose is equals to 200. Sorry, how much? 180 gram. 180. So 180 gram, right? So you just convert this to mole first. So I put this factor to get moles. So mole, I put mole up here and 180 gram down here. So gram cancel. So I get 250 multiplied by 1 divided by 180 gives you 1.4 moles. 1.4 moles of glucose. How much glucose I have? 1.4 mole. First of all, I converted that 250 into moles. Make sense? Easy. Now, I have 1.4 moles. So I have how much glucose here? 1.4. So I have 1.4 moles of glucose. And how much, what is it asking me? How many gram of oxygen is required? So how many gram of oxygen is required? He is asking me to calculate oxygen. So I put oxygen here, X. I don't know how many mole of oxygen I need, right? Yeah? We want to find this one. Now take that ratio. X by 6 is equals to 1.4 by 1. So X is equals to 1.4 multiplied by 6 divided by 1 moles. How many moles it comes? 1.4. That comes to be 8.4 moles. 8.4 moles of oxygen. Any question? 8.4 mole, right? Now, oxygen. So can you convert this into gram? Easily, because one mole of oxygen, look the periodic table, 1 mole of oxygen, 1 mole would be equals to 1 oxygen there is 16, 2 oxygen would give you 32 grams. So you can convert this mole into grams, right? So that factor in such a way that you get a gram, 32 gram here, 1 mole down here. So if you want to mole cancel, 8.4 multiplied by 32, whatever number gives, that many gram of oxygen we need, right? Easy? So it's good. So if the question asks you how many moles of carbon dioxide you produce, so you would do like this. So how many moles of carbon dioxide you would produce? If the question was how many mole of carbon dioxide you would produce, you put X here. So X by 6 is equals to 1.4 by 1, and then you solve for X, right? If the question asks you how much water is produced from the reaction, put X here, then just calculate that, right? 1.4 by X by 6 equals to 1.4 by 1, and calculate the moles. This is moles, and if you want to convert into gram, multiply by that factor, right? 1 mole of water is equal to 18 grams. Easy? So just like that. Now, I'm not going to do numbers. Slide number 6 is exactly the same. You don't have to find the limiting reagent here, so you can practice yourself. Yeah. Now let's go to 7. Slide number 7 is exactly the same, so you can do yourself. Slide number 8. You can try yourself. It's nothing new. Yeah, just find that, put the ratio and then calculate that one. Slide number 9, exactly same thing I take from the book. Yeah, so you just put those number. If you don't know, you can just email me. Yeah, so it's exactly the same thing. Just what is known, take those ratio. What is not known, put x and x by that and solve for x. Right? So I already did those, and you can try those yourself. Here is a problem. I just this is a big problem. So you can try this one. This is slide number 10 and 11. There is one problem. I already solved it. It's a big number. You try that one, but I help you. One, I put that in homework. I am just going to practice this homework problem, right? Yeah. So try that. So from the today's lecture. So I'm in the today's lecture. So this is the lecture hard in Canvas. So all other thing there you can solve yourself here. So let's work with the today's lecture. So I'm in the slide number 1 from today's lecture. Yeah, slide number 1. So no question here. So now there are two things: theoretical yield, theoretical yield. Yield means produce, how much we produce, theoretical yield. So theoretical yield versus percent yield, YIELD, percent yield. So if you do the reaction say, okay, you will get 50 gram of water. The reaction says 50 gram of water, right? But when you really do the reaction, you only get about 20 gram water. When you go to the laboratory and do the experiment, you get about 20 gram water by mixing something, right? But your reaction says, oh, I must produce 50 gram water. So this is called theoretical. This is called theoretical. So you did some calculation. It comes from the calculation. So whatever the stoichiometric calculation we have been doing from already in this class, that's the calculation. Whatever that gives is the theoretical yield. So how many gram of water I produce if I mix 2 gram of hydrogen in 4 gram of oxygen? I do calculation and I find this one. So this is called theoretical. But I go to a laboratory and mix that many chemicals and try to and produce water, and I only get 20 grams. So this is real, actual. So this is called actual. So actual is always a smaller number than the theoretical, because theoretical is the theoretical, right? Because that's said by the equation. But actually, when we go to do the lab in laboratory, this number is always, actual number is always smaller than theoretical. Make sense? So theoretical is the product calculated by using the equation. Actually is we go to the laboratory, mix the chemical, and how much product we get. That's the actual production. Yeah. Now, percent yield. What is percent yield? Percent YIELD. Percent yield. So percent yield is, so this is you could produce in laboratory. So this number actual amount divided by theoretical amount. So this theoretical amount and multiply by 100. So like that. So to 40%. So you should be expecting to get 50 gram, which is 100%, but you only get about 20 gram, and that is 40%. So you only could get 40%. So other 60% of the chemical is just either not pure, or the reaction didn't happen correctly, or something didn't work right, or it's a human error. So there are many things which lowers the product. Make sense? Yeah. So theoretical yield is always higher number. Actual yield is small number because there are a lot of errors during the experiments. But in calculation there is no error, right? Make sense? So this is how we calculate the percent yield. So this is in this reaction, you mix hydrogen and oxygen, and you did reaction, you produce some water, and you are expecting to get 50 gram of water from this reaction by calculation, but you only got 20 gram on doing the actual reaction, right? So this is the actual 20 gram. This is the theoretical. So 20 by 50 gives you, that's actual by theoretical gives you the percent yield. Make sense? So why percentile is always smaller than the theoretical yield? Because in percentile we really need to work. It's not the math, right? So maybe the chemical are impure. Maybe there are other things are being produced. Maybe reaction did not complete. So there could have been many things. So now let's do one problem in slide number 2. So this is the homework problem. I just changed the numbers here. So what I'm doing here is some numbers, but in exam, in homework, I just changed the numbers. So here I'm using 50 gram. There I'm using different numbers. So let's look this slide number 2. So here is a reaction. So here is a reaction. N2 plus H2 produce ammonia, NS3. N2 plus H2 gives an ammonia, right? Now, is it balanced? Not balanced. We must balance first. So let's put 1 here, 3 here, and then what else here? So 2 here. So now it is balanced, right? Now this is a reaction vessel. This is a reaction vessel. How much ammonia? How much nitrogen and hydrogen you are mixing? 50 gram of nitrogen and 50 gram of hydrogen we are mixing each, right? So here in this one, I mix 50 gram nitrogen and 50 gram hydrogen. But it doesn't say which one is more, which one is excess, which one is in this case, right? Now we need to find which one is the limiting reagent first. So that's a little bit difficult there. So now we need to convert this into moles. So 50 gram would be, I'm going to convert this into moles. So 50 gram, this is nitrogen. But if you look at the periodic table, 14 gram, 1 mole of nitrogen, 1 mole nitrogen is equals to 14. 14. So you look at the periodic table, 1 mole N2 is equals to 14. 1 is 7. So 14 or 28? 28, I think. 28. 1 is 14. To 28, I think it's a 28. 28. 28. 1 mole hydrogen is 28. And then how about this one? 1 mole hydrogen. 1 mole hydrogen is equals to 2. 2, right? Look at the 1 hydrogen is 1, 2 hydrogen is 2, right? Good. So convert this to mole first. So 50 gram nitrogen. So I have 50 gram. So the conversion factor is this one. 1 mole nitrogen equals to 28. So 28 grams. So I put the gram part down here and then 1 mole up here. So from this one, 50 by 2.8 gives me 1.78. This is 1.78 mole of nitrogen. I have 1.78 mole of nitrogen. 50 gram of nitrogen means 1.78. Makes sense? Now do this hydrogen. For this hydrogen, so 50 gram, I want to convert this into mole. So 1 mole of hydrogen is equals to 2 gram, right? 2 gram. So 1 hydrogen is 1, 2 hydrogen is 2. So I put this 2 gram here, 1 mole here. So that is equals to mole, sorry, gram cancel. So 50 by 2 would be 25 moles. 25 moles. So how many hydrogen I have? 25 moles hydrogen I have. How many moles nitrogen I have? 1.78 moles I have, right? So from there, I can find which one is the limiting reagent, right? So I can start from somewhere here. So I just take one. So let's take hydrogen. So hydrogen, how many mole hydrogen I have? 25. I put 25 here, right? Make sense? Moles. So that many moles of hydrogen I have. For 25 moles, how much nitrogen I need? I just put X there. I'm just calculating. Oh, I have a 25 mole hydrogen, and now how many mole of nitrogen I would need? So I just take this ratio. X by 1 is equals to 25 by 3. X is equals to 25 by 3 multiplied by 1 is 8 point. How much? 8.3 moles. You see, how many for 25 moles? I have 25 moles here. Hydrogen, and I have 1.78. But for 25 mole of hydrogen, how many mole of nitrogen I need? I need 8.3 moles of nitrogen, right? Make sense? So for 1 mole of nitrogen, I need 3 mole of hydrogen. But for 25 mole of hydrogen, how many mole of nitrogen I need? So I calculated 8.3 mole. But how many mole of nitrogen I have? I need uh, I need I need 8.3 moles 8.3 moles nitrogen to react with react with 25 mole hydrogen 25 moles hydrogen, right? So that's what it is saying. 8.3. I need 8.3 moles of nitrogen to react with 25 mole hydrogen. But I have how many moles? 1.78. So 1.78 moles nitrogen. So short supply. You see. So I need 8.3 mole, but I have only 1.78 mole, right? So nitrogen clearly is a limiting reagent. Did I make it clear? It's a little confusing. You need to practice a couple of times. Yeah. So I need 8.3 mole for 25 moles, but I have only 1.78 moles. So you see, I need a lot to react with 25, but I have only this much. So this is the limiting reagent. So nitrogen is limiting reagent. Now my calculation should be starting from the limiting reagent. Now I'm going to use this one, and so my limiting reagent is this one. So I'm going to put X here, and how much ammonia I need to produce. That's what the question is. So all right. So I put X. Sorry, how much? Sorry, this is not X. So how much nitrogen I have? 1.78. 1.78. And then how much I will produce? I put X here. Make sense? Because I have 1.78 moles. It is a limiting reagent I found from previous calculation. So how much ammonia would I get? I just take the ratio. X by 2 equals to 1.78 by 1. This is just too much. We don't do the reaction calculation from X's. Yeah? Nitrogen is X's. So now X is equals to 1.78 multiplied by 2 divided by 1 is 1.78. Multiply by 2 divide 1 would give me 3.56 moles. 3.56 moles. So how much ammonia I will produce? 3.56 moles. Can I convert it to gram? Yes, easily, right? So 3.56 gram, 3.56 moles ammonia I produce. Now I convert it to gram. So look at the periodic table. 1 mole ammonia is equals to 17 gram. Nitrogen is 14, hydrogen is 1 and 14, 3 and 14, you get 17 grams. So I convert to moles to gram. I put the mole part down here, the gram part here, 17 grams here. So mole cancel. So 3.56 multiplied by 17 gives you 60.52 gram. 60.52 gram. Yeah. So that is. Is this actual? This is actual L or theoretical L? This is a theoretical L. How did? Because I have not. I didn't go to lab and did the experiment yet, right? I don't know. This all are theoretical calculation I am making. So this much gram of the ammonia I need to produce if I did this reaction, right? But the question says, oh, I did that and I only got 30 gram of ammonia in actual experiment, right? So that's the actual yield. So actual yield is, so actual yield there is 30 gram. So this is theoretical. So this is theoretical. I just did all calculation and I said this much chemical ammonia I should be getting, right? Make sense? But the question is saying, oh, somebody go to lab and try to do this reaction with his hand and he only got 30 gram of ammonia. So the actual yield is actual actual yield is 30 gram. So this is 30 gram. So somebody go to lab and did this reaction, mix the 50 gram of hydrogen and 50 gram of nitrogen and did all kind of the work in the lab and he got only 30 gram of ammonia. But he's supposed to get 60.52 gram of ammonia by theoretical calculation, right? Now we need to calculate the percentage. So this is actual, now percentage. How many, what percentage he could get? Percentage is 30 gram. He got out of 60.52. He should be getting, he was expecting to get 60.52 gram, but he only got 30 gram. And then you multiply it by 100, and that gives you, in another slide, 49.5%. So 49.5%. He was expecting to get 100%, that is 60 gram, but he only get about 30 gram, which is 50%. Yeah, so 50% efficiency is the reason. Make sense? So one difficult thing here is to calculate the limiting reagent. Once you know which one is the limiting reagent, you can easily just put those fractions and solve those, right? Easy. And you can easily convert the mole to gram, gram to mole. That's the thing we have been doing from the very beginning of this class. So this is the homework problem I put in the homework 4. Yeah. So there, here I am saying 50 gram, but there I just change the number. Once you know one reaction or one problem very well, you can just use that theory in all chemical, right? All chemical equations. So we need to understand just to do one thing very well. Now let's go to slide number 4 from today's lecture. So in slide number 4, there is a sodium sulfate bottle. So this is called a gravimetry sodium sulfate bottle, Na2SO4. This is a chemical. Chemical cannot be bought in pure state. We call this a sodium sulfate, but maybe there is some water with this one, or maybe some copper is mixed, or maybe there is some iron is mixed. So this chemical is not pure. Yeah. So this the company put the label here, and it says, oh, this is the sodium sulfate, 98% pure. It says, oh, that is a 98% sodium sulfate, and the rest maybe there is maybe copper, maybe iron, maybe something else, maybe some water, right? So what is the purity of this one? So our job is to find the purity of this sodium sulfate. So what he did is, he took 0.498. So let's write the reaction first. So it takes 0.498 gram sodium sulfate and then react with the barium chloride. So he took that sodium sulfate, Na2SO4, and then he reacted with barium chloride. This is barium chloride, and the reaction becomes just he exchanges the position. So Na goes with Cl, Na and Cl sit together, Ba and SO4 sit together, Ba and SO4 sit together. So this guy is a solid. So what he did is, from here he took 0.498 gram and then put in the beaker 0.498, put that in the beaker and add some barium chloride here. Add barium chloride here, and the reaction happened. And he at the end he just tried this and tried to find how much barium sulfate he got. So barium sulfate he got was 0.541 gram. So 0.541 gram. He got 0.541 gram reacting with 0.498 gram. So he takes 0.498 gram of this one and react with a lot of barium chloride, and he got this much of this one, right? It's in terms of gram. So he did it in gram. So in this reaction, it's a little bit difficult to work in the gram, so we convert those into moles, right? Moles. So it's already given here. 1 mole of this one, 1 mole of BaSO4 is 1 mole of this guy is equals to 233.4. So you can calculate it, but I just already put it there. So 1 mole of BaSO4 is 233.4 gram. So I convert this gram into moles. So I put a mole part up and then the gram part down, 233.4. So how many? So grams. So gram cancel. So how many mole is this one? So let's calculate this one. 0.541 divided by that gives me barium sulfate. So this is 2.32. This gives me 2.32 10 to the power minus 3. So that many mole. Make sense? So I put it that here. So there is one. I have this number here. So that many mole I make. So last year I was taking, I put this question in exam. Most of the students could not do, very few could do it. So let's see if we could understand more this time. So that many moles. So I just convert this gram into moles there. Now, uh, so this is very pure, this is impure. So I took this much, but I don't know if this is the right amount or not right amount. So what I do is, so I one here. So I want to find how much I would need. So I had here was a how much gram that was? That was a 0.541 gram, which is this many mole. So if my final product is this much gram or that many moles, how many moles of sodium sulfate I should take to get this much mole of barium sulfate? That's what we want to calculate, right? Yeah. So how much I need? So I need this mole to get this mole to get 2.32 10 to the power minus 3 barium sulfate. So I need this X. I need X mole of sodium sulfate to get 2.32 10 to the power minus 3 mole of barium sulfate, right? So what is this X? That's I want to calculate. X by 1 is equal to this 2.32 10 to the power minus 3 divided by this 1. So 1 cancel. So X is equals to 2.32 10 to the power minus 3 moles. So how much sodium sulfate I need? That much, that many mole, right? Now I can convert that mole to gram, right? So sodium sulfate. Now from the barium sulfate, I just found how much pure sodium sulfate I will need. So that much sodium sulfate I will need. Now I'm going to convert this into gram. So in converting the gram, I already put the conversion factor there. 1 mole of sodium sulfate equals to 142 gram. So mole, 1 mole, I need gram here. So I need gram here. So I put the gram part of. So the equation is this: 1 mole is equals to 142 gram of sodium sulfate. Sodium sulfate. Sulfate. So this is a mole. I'm going to convert that mole to gram. So mole, I put up 142 gram, 142 gram, and then 1 mole. So mole cancel. So you multiply this with this one and get how many gram of sodium sulfate you need is 0.329 gram. 0.329 gram. Yeah, barium sulfate. How much sodium sulfate I need? 0.329 gram sodium sulfate I need if I produce this much pure barium sulfate. Yeah, so this much pure. If this bottle was very pure, I would need to with that 0.329 gram, but not 0.498 gram. But this is impure, right? So what is the impurity? We need to calculate there. So impurity is equals to so so impurity is equals to I percentage purity. Percentage purity. What is the percentage purity here? So if it is a very pure, I did this much 0.329 out of 0.498 gram. 0 multiply by 100. So this gives you 66%. So this is only 66% pure, not 98%. This is 66% pure. So rest is maybe water, maybe copper, maybe iron, maybe other things, right? So this is called the gravimetric analysis. So we mix the chemical and we get some precipitate, and that precipitate we dry and measure, and that's pure. And from that purity, we want to calculate. Okay, how many gram I started with the impure. So impure I took 0.498, but if it was a pure, I would only get 0.329 to get this much. So this pure amount I would need divided by the impure amount I took out from the bottle and multiply by 100 gives you the percentage purity. Just try a couple of times, yeah? It's a little bit confusing, but you will do this kind of work in future class, maybe 213 other class, gravimetry. So this is just the beginning here. So I put one problem like that. I didn't put this as a homework. I put only the previous problem as homework. Yeah. Good. So it's very important. So it's all calculations. So that's how sometimes we find the percentage purity. Now, even more important than this one is the today's lecture about the molarity. So the molarity is probably the single most important subject in the chemistry. If you go to the work, you must need to know this one. Now, what is molarity? Molarity. So I am in the slide number 5 today. Molarity. This is a very important. So molarity is M. So molarity. First of all, take one chemical. Take a chemical. Take a chemical. So we are talking about, let's say, sodium chloride. Sodium chloride. Find the molar mass. This is a chemical, and find molar mass. Molar mass. Maybe I just use the sodium bicarbonate. Sodium bicarbonate. So sodium bicarbonate, I put in the exam. This exam one, you already know. What is the molar mass of sodium bicarbonate? It's 84, right? 84. So 84. So find the molar mass. So 1 mole of sodium carbonate, sodium bicarbonate is equals to 84. If you remember the exam, so that was one of the exam problem, right? So you did, I think pretty much everyone did right there. 1 mole of sodium bicarbonate is 84. So what you should do is take 1 liter vessel. This is a 1 liter, like this. So this is a round bottom flask, and they got a mark here. So it is 1 liter mark. Yeah. So what we should do is we should go to take the bottle of the chemical and measure for 84 gram. Measure MEACURE. Measure 84 gram of this guy and put it here. 84 gram. 84 gram, and then add water so that it reaches to 1 liter, and then shake it. That's called the 1 molar solution. Make sense? First of all, you take the chemical, find the molecular mass, and then or molar mass, and measure in gram equal to that molar mass, and put in 1 liter flask, and then put water to make the 1 liter. Yeah, so that is called 1 molar. That's how we make the 1 molar solution. 1 molar solution. So I just talk about the sodium bicarbonate. How would I make the sodium carbonate 1 molar solution? 1 molar. So 1 molar. I just make 1 molar solution of sodium bicarbonate. Now I want to make this 1 molar solution of sodium carbonate. 1 molar solution of sodium carbonate, Na2CO3. So you already did this in homework. So 1 mole of sodium carbonate is equals to I think 106. You already did 106 or 206. I think it's that's 46. Carbon is 12. Oxygen is 48. Yeah. So it's a 1. Yeah, it's a 106, right? So this was in homework problem, right? So molar mass of sodium carbonate is 106 gram, right? So go to the lab, measure 106 gram of sodium carbonate in balance, and then put in the 1 liter flask here, 106 gram, and then add water, and then put up to 1 liter. So yeah, easy. So that is 1 molar. So this is the definition of 1 molar. So if you take half, so if you take half of this one, this also becomes the half. Half of the 1 molar is 0.5 molar, right? If you take twice of this amount and put it here, that becomes the 2 molar. Yeah? Make sense? It's very important how to make the molar solution. Now, this is a formula, so you don't have to understand this all, but here is one formula. So molarity is equals to molarity. Molarity is equals to number of moles divided by liter. How big this vessel is? LITR, liters. So this is the molarity. That's how we calculate. Yeah. So how many gram I took? 106 gram. 106 gram is one mole, and I put 1 mole here, and I put in 1 liter. So 1 by 1 is 1 molar, right? So this is the formula. So you can easily apply this formula and find the molarity. So let's go to slide number. How much is that? Slide number is that is 7. Let's go to slide number 7. Slide number 7. let's go to slide number 7. This is says you took 0.395 gram of potassium permanganate, KMnO4, potassium permanganate, and added water to a 250 ml. So 250 ml water, 250 ml solution or water. So you see, now what is the molarity of this one? We need to find the molarity. So what you did is, you took the bottle of potassium permanganate, KMnO4, and then how much you put in this bottle? How much you put it? 395 gram of this one, you put it here, and added water to make not 1 liter, you just to make 250 milliliter here. So this vessel is not 1 liter, this is 250 milliliters. Make sense? That's what they did. Because in laboratory, we don't have 1 liter vessel always. Sometimes we have 25 ml, sometimes we have 50 ml, right? Sometimes 250 ml. So what is the molarity of the solution? First of all, what's our formula? Molarity is equals to number of moles divided by liter. Number of moles divided by liter, right? Now we need this in liter. So this 250 ml, we need to convert into liter. First, we need to convert that. We want to use this formula. So we want to convert this into liter. So 1 liter of anything is equals to 1000 ml. 1000 ml, right? 1 liter of anything is 1000 ml, right? Now I need to convert this ml to liter. So 250 ml I have. So I want a liter. So I put this factor in such a way that I cross the ml. So 1000 ml down here, 1 liter up here, right? Just the conversion. Now ml cancel. So 250 by 1000 gives you 0.250 liter. Yeah. So 2.50 liter. So I put 0.250 liter here. So this is liter. Yeah. Now I need to convert this gram to moles, right? Moles. So potassium permanganate molar mass is given. 1 mole of potassium permanganate is equal to 158. So 1 mole of, I just finished this one. I put that number here, and then now let's do this one. So 1 mole of, I go here actually. 1 mole potassium permanganate is given. 1 mole potassium permanganate is equals to 158 gram. They are writing 158.034. I just write 158 there. So this is the gram here. 0.395 gram I have. So I put this. I need a mole up there. So I put a mole here. I don't need a gram. So I put the gram here. Now when I do this, I cancel this gram. Now this multiplied by 1 divided by 158 will give you how many moles there? So 0.0025. 0.0025 moles. So I convert grams to moles. I convert milliliter to liter. So liter I already put here. Now I am going to put that mole there. 0.0025 moles. So mole here, liter here. Now I got the molarity. So how much is this divided by this? I get 0.010 molar. So our job is just to convert the volume to liter and gram to moles and divide mole by liter, right? See, we are doing the same thing always, right? Liter to milliliter, liter or mole to gram to mole. We are repeating the same thing, but different purpose, right? Sometimes we do this, sometimes we do that, but always we do the same thing. So it looks like we are talking the same thing from the very beginning of the class until now. And when we finish this class, we will be still doing the same thing. Mole, gram, mole, so just like, but with just a different purpose a little bit. Yeah, make sense? So you are given the gram, convert that to mole. You already know how to convert gram to mole. You are given the milliliter or anything, convert that to liter and divide that mole by liter, and that's the molarity of the solution. Yeah. So let's see. Now let's look the slide number 8. It's the same thing. If you look at slide number 8, 5 gram is given, and then molar and then mole to gram conversion factor is given. Convert that to gram to mole, and then 250 ml of solution. Convert that 250 to liter and divide mole by liter, and that's a molarity. Yeah, same thing. So 8. So I'm not going to. I already did this in the slide there. You can just read it. Yeah. Now here a couple of things here. I just want to mention in slide number 9. Slide number 9. Slide number 9. So I have a beaker here. In this beaker, I have a substance of solution is CuCl2. So I have a water here, and I put some copper chloride there and dissolve it, right? And then the molarity of this solution is 0.30 molarity, 0.30 molarity solution. So where does that number come there? So how much gram he put? He converted to moles, and then how much is the solution? He converted to liter and divide the mole by liter, and he got 0.30 molarity of this solution, right? Now the question is, how many mole of copper is present? So how many mole of copper is present? Copper has this 2 is coming from the head of this one, so this is +2. How many mole of copper is here? You see here, copper is only 1, right? Only 1. So copper is only 0.30 molar. But you see here the chlorine, where the 1 coming from? It's coming from the head of this chlorine. So chlorine is -1. It is a 1, so it's a -1 there. Now, how many chlorine are there? 2. So 2 multiplied by 0.30 m. So that is equals to 0.60 molar. So if you have to look if you are saying, okay, what is the molarity of the copper chloride solution? You are going to say 0.30 molar, right? And if you want to look the individual, how many molar copper is there? I have 0.30 molar because it's only 1. 1 multiplied by 0.30 is 0.30. But how many moles of chlorine I have there? How many? What is the molarity of the chlorine solution there? Cl. So that I have 2 here, so I multiplied that number by 2, double. Yeah. So if there is 3, you multiply by 3. If there is 1, just multiply by 1. If there are 4, multiply by 4. Right? Good. So how about here in the 10? So in number 10, they are saying 0.10 KCl, 0.10 m KCl. So what is K plus? 1. So K plus is just 1, 0.10 m. Cl also is a 1, so 0.10 m. Yeah? So there is a 1 in 1, so I just multiply by 1 by 1. How about second one, 0.25 MgNO3. So I have here 0.25 MgNO3. So you see now, so Mg has only 1. So 0. Mg is just Mg ion. Mg. So this 2 is coming from the head of this one. So we write the ion like this. So it's only 1. So 1 multiplied by 0.25, 0.25 more. But I have NO3. How many NO3 I have? 2. Right? 2. So NO3. So how much charge is NO3? So if it's a 1, it's coming from the 1 here. So -1. So how many NO3 I have? 2. So 2 multiplied by 0.25 is 2 multiplied by 0.25 is 0.50. Yeah. So the molarity is given. Just look the how many it is in the foot. You just multiply by that number. Easy. Not how, right? But there will be this kind of one of the question will be this typo. I might put something in take 1. If there is 1, multiply by 1. If 2, multiply by 2. So like that. I think we have still a couple of slides, so maybe we stop today. So in the next class we discuss the rest. Yeah. So let's see if they have any comment here. I don't know. Maybe looks like I already stopped.